Okay, good afternoon, everybody. We have a faculty candidate, Dr. Pande. He is, I think, one of the outstanding researchers from our candidate pool. He published quite good number of papers in transaction papers and other things. And he got his bachelor degree in 2007 in IIT India. And after 3 years, he got his PhD from Iowa State University. So I don't know what was his magic to having a PhD degree in 3 years right after bachelor degree. So you will see how his research outcomes. And he has lots of awards, but one of the outstanding one was NSF Computational Innovation Fellowship from 2010 to 2012. That's a very prestigious fellowship available in US. And currently he's a postdoc researcher in University of California, Davis. And he also very active in a number of international conferences and other publications. So let's welcome candidate with the bootcamp.
Thank you very much. So, good afternoon, everyone. And he already gave me a long introduction of me. So, I do work in computer engineering and computer science areas. And I'll be giving this talk today on improving mobile applications using data-driven models. So, if you have any question, please feel free to ask because I have only 1 hour and I can just speak for 1 hour. I have no problems. So if you have any question, please ask me in the between, and I'll be happy. And I can, adjust my speed accordingly. So, but the basic plan is I just want to give an overview of my overall research and how it fits with the big data ecosystem, and then discuss about 2 of the problems we have been working on. The first one is in the video quality of experience assessment in mobile devices. And the second one is in the health informatics, where we try to understand the energy expenditure or the calories out of a person using mobile sensors, including a smartphone. And then I just try to summarize. So that's the basic idea. So basically, I was just trying to think when I was preparing these slides, why did big data came into being? The way it happened in the 90s, we were using paper forms in all the government offices, in all the companies. So the number of data online was very few. It went to 2000 when we have the smartphones and everything, slowly phones and smartphones coming, the era of internet, more and more online things. And around 2005 and 10, we had smartphones generating volumes and volumes of data, right? And now, along with the internet, we have a plethora of data coming to the cloud, and it's not possible to just make sense of such a huge data sets with the human intervention. So we need automated machine learning algorithms to make sense of it and drive inferences back to the application. And then in the next few years, it's going to be the era of Internet of Things, where your your microwave, your refrigerator, your wristband, your shoe, everything is going to be connected to the internet. And then you have tons more of the data from exascale to the higher scale. I don't know what they call it right now. And that data, you don't know how to mine it. So that's the era we are coming. And as it came, around 2000 came the word of data-driven science, and becoming more and more popular now. So that's the basic evolution of, if you see here, that we have the connected devices all around us. And we have a lot of data coming out. Just trying to give us some statistics in networks, because that's a background I work from in most of my things, my projects. So we had 7 billion mobile users in 2013, and obviously some people have more than 1 phone, so it's fine, but it's still a very huge number. And we had 19 exabytes. Exabyte is gigabyte. So we had 19 exabytes of data traffic in mobile cellular, not Wi-Fi, in cellular in 2013, and it's predicted by the Cisco VNI report to go like 10 folds in the next 5 years. So it's a very huge amount of volume going. And if you see the picture, it's a picture of the YouTube or Netflix on a tablet. That's where most of the consumption is. Around 70% of the traffic in mobile, 60% today and 70% by 2018, will be videos. So that's the current area where most of the network traffic is going. And if you go to the future, IDC predicts it should be somewhere around wearables, healthcare, and not, because healthcare, especially in the United States, is going to be a very significant, place where they have lack of funding or resources, and they need much and more automation. So I'll be going through two of the projects today on the two sides on video and healthcare, a little bit of what I've been doing. So going next, I was just trying to summarize for myself, and I'm just showing the same slide. What are the big data operations we need for a full system which does that in a real-time analytics way? The first thing will be to collect the data. Many times we forget that. But that's actually very important because it requires a coherent approach to hardware, networking, sensing, and security. Because if you don't do it, the sensors may die after a few days, like it. Even in wireless sensor network, which has been a traditional area, we study all these things. But if you say body sensors, people are using smartphones nowadays, and the wristband. Microsoft launched Microsoft Band. I don't know if you're aware of that. iWatch, I think most people will be aware of. Apple launched it. It will be coming next year. So you have an iWatch, you have a smartphone, Nike shoe sensor, everything connected and all those things. And all the data is going to the cloud. They're mining your behavior and even using it for research. So that's a good example. Now the thing is, if your phone dies, you can recharge it, but people like to keep the wristband throughout the day or throughout the weeks actually. So we have to come up with the robust ways that these devices interact and coordinate so that when your phone dies, you don't have a problem. It takes over the sensing part, at least parts of the sensing part. Or when you're wearing a wristband and you're wearing a smartphone, might be just let it sleep and let him do the sensing, because you're going to. So we have to do all these behavioral approaches into the sensing and the collection so that it is more efficient. That's the basic idea I'm trying to drive home right now. So it's not just a traditional way of doing the networking or sensing, but seeing it in the human perspective and the way we are collecting data to make it more and more reliable. The next part is the data processing side, where you have storage, database, and hardware acceleration on the cloud and all those different issues there. The third is data analysis, how to make sense of the data which you've collected and analyzed in your database. We need machine learning, signal processing, statistics, and other algorithms definitely to do that. And the fourth part is the execution, to bring the data back to the domain, the results back to the domain, and drive the results for the industry behind it. So some of my research has been across these things, so I'll just try to summarize that before I go to the specific examples. So I do work in networking. Optimizing wireless network performance has been one of my focus. And we design, for example, actually this is under revision, is the first paper, where we try to find a new MAC which can sit on the top of 82.11 N or AC, and it gives like 60%, 50 to 60% improvement in both throughput and delay over the existing Wi-Fi. But it is optimized for video traffic only. So that's an example of application-specific acceleration which you can do. And well, the idea we got it from this was like we have Hy-Vee for food or Best Buy for electronics. So why not something like that for video? So we want to push it to we were trying to push it to a VMAC or a Wi-Fi where you can have separate hotspots. We do have now like Chromecast. Google's Chromecast is a video hotspot sort of a thing. So shouldn't we have different protocols for them so that they are more efficient, low power, and do a more ubiquitous task of sensing or providing data to you? So that's one example. Then implementation of Android, obviously, that's because that's the most common smartphone platform to test our applications. Then sensing, I'm working on optimizing data application performance using sensors and drawing inference from the sense data. And we had a very good paper, I'm not mentioned it here, but one of the paper was, I think, when you're, for example, watching a video on your smartphone, right? So earlier, if you had a Skype chat, you went to your desktop or a laptop, sat down and had a video chat with your home. Nowadays, people are talking on a smartphone, and what it leads to is you're moving most of the time. And we found it leads to a lot of quality loss. And it's actually, if you see in traditional sense, it's the reverse of what was happening even in the industry, because now the required content is static and the background content is dynamic, right? Your background is moving, you're not moving, and relative to the camera. So if you can use efficient techniques now, we can actually optimize the network, which has not been done at least in the existing codecs. So we did this paper this year in SECON, and we had to use machine learning techniques to basically sense all these things on a frame and see how much redundancy the network needs for different type of the frames. low motion frames, high motion frames, and things like that. So that's about sensing. And security, device and user authentication, fingerprinting, encryption, localization. Interesting aspect of security in terms of sensing is, let us say you're collecting data from, I'm not talking about the internet, the information assurance and the traditional security, but some of the focus of my work is like, if you have a smartphone for sensing your data, there was a paper actually this year, I think, on NDSS, which says that we can uniquely identify the user using the smartphone accelerometer, because the accelerometer has a inbuilt noise or some features which can be extracted using machine learning, and that can be used to identify whose data is it. So let us say you have two apps, Fitbit for your own app, and your hospital gave you another app. Those two apps can collude to infiltrate your privacy now. So, because both the apps are running in the cloud, okay? So it's a security problem. The data is sensed from your phone for different applications. One might be in your office, one in your personal life, one for your health or something like that. So different sensors have so sensor-specific security problems I'm trying to say here, which is specific to sense. Similarly, there's a security problem in the cloud where you want to have homomorphic encryption and things like that, so that you can have operations, mathematical operations on the encrypted data instead of decrypting them and things like that. So going next is data processing, hardware acceleration. I have been working on hardware acceleration on FPGAs, which I use in some of the supercomputers for accelerating the data implementation task. Data analysis, so using decision trees and neural networks and other models to model the nonlinear relationship between the input features and output vectors. And signal processing, in this I use wavelet and Fourier transform for efficient signal processing and hardware amenable implementation. So that is the basic idea. I was just trying to give a brief overview of how I feel my work fits into the big data approach. I'll just try to give an example of the video QoE assessment in mobile devices. So there's a trend towards QoE from QoS. QoS was a network quality of service, where we used to focus on the packet loss rate, the network parameters like packet loss, delay and jitter and things like that. The QoE means what is the quality experienced by the human observer. Okay, it's the visual quality. It's not, we're not talking about the network parameters, but what is the experience of the user. That's what we're trying to focus on when you say QoE. So this is data from Cisco that is existing in the obviously projected, that most of the traffic is coming from smartphones and laptops, which are very small mobile devices for video consumption. And if you see, mobile video is projected to have a 70% share here. So it becomes very good if we can actually find a metric to estimate the QoE of the videos. Why? So this is the system which is working. You have content providers like ESPN, YouTube, Hulu, Fox, and other studios. They're providing the video content, which is provided by companies like AT&T and others, but it is cached by inbuilt companies like Akamai, Limelight, which cache it in different portions of the network so that you can have almost real-time access. And then it's watched by users. When you click on the advertisement, it generates revenues for these companies, and they share the revenue here. So that's the system model which is working today. But we don't have any feedback in terms of the quality to the content provider or the CDN from the user. So we don't know what actually the user is watching when he's watching a YouTube or any Netflix video. You clicked on it, whatever network is available, it is streamed according to that. It can be a delay and all those things. So if we have QoE, it helps us at different levels. For example, the user, he can say, I'll pay for the quality I get. I don't care whether it's, your CDN is Akamai, it's in Omaha, or whether it is in California. I just care it should be real time and it should be good quality for my device, right? So right now what you do is you pay $100 to Verizon for your cellular data, and you pay $3 to YouTube to buy a video, and you start playing it, and if it doesn't get a good quality, you can't complain. But if we have a QoE model and an assessment in the mobile device, we can say, see, I got only this quality of video. We have objective assessment of the video quality. So then you can say, I'm only going to pay that much. So we can even change the video distribution model. How it helps the companies like YouTube, because they know what is the problem you are facing. So they can actually coordinate with them and change the system the way they're doing, or change the bit rate, change the resolution, and change the parameters dynamically so that the video is streamed properly to you. So it allows the content provider, and they can also choose which CDN is giving them a better service. So it helps us to objectively evaluate the entire system if you can do an end user evaluation properly. So, and obviously it's an obvious question, why is it so difficult to measure the online video quality? It should be pretty straightforward, you know, but so we have many schemes. So one of them is the subjective scores. So you ask people, give them a device, give them some test videos, you ask them to rate 1 to 5, good quality, bad quality, and all those things. But you can't do it in real time for all the videos, right? There are millions of YouTube users and all those things. So you can't do it for every person. After every 5 seconds, you won't ask him, you know, he'll be more irritated. So the QoE is actually reducing. It's not increasing anyway. So basically, although they are the best measure, you can't do it. So we try to develop some regression model and try to measure some objective metrics. Now the objective metrics have been there for like 30 years, research by the community. And there are many metrics like VSNR, SSIM, PSNR, and all those things, which are pretty good. But most of them require original video. So when you're watching, you don't have original video. That's why you're streaming it, right? So you cannot have any contact with the original video. So how can you get these values? So we can't use these. We can't use these. There are some no reference metrics like blocking, blurring, but they are very inconsistent with the user experience. And they're very specific to the distortion you're having. If you're having blocking, this metric will detect it. If you're having blurring, so there are a number of distortions which happen: ringing, blocking, blurring, freezing, and buffering issues. So we don't have metrics to do that accurately. There are other metrics. This is the objective, the QoS metrics like buffering, bitrate switch, average bitrate, which have been used by some people from AT&T and the AT&T Research Lab and people like that to estimate the user's quality. But again, they are only measuring the network. They're not measuring what user actually saw. And there have been, I think, 2 or 3 papers on user engagement. It's mostly from actually, there's a guy, Ian Stoica, I think, in Berkeley. He has a startup, Conviva. So they have a very big, it's a company with a very big setup in industry. So they have really very big access to the data sets for video. So they have like 40 million users per hour, per day, or per month. So they use that data sets to publish this research. But the problem is they are using the server-side traces. So the server knows, the server is collecting what is the network bandwidth and bitrate and all those things. And they know when the user started the session and ended the session. So if I downloaded a video and I watched it for 5 minutes instead of the full video, then they'll say it is this much percentage the watch time, so the engagement is low. These metrics are ambiguous in the sense that, you know, you don't know it's a QoE or not, because you might be your friend came, might be you like some other video better in terms of content, or might be something else. You wanted to go for an assignment or a class. So there can be many reasons. That's not engagement is not same as QoE. So what we wanted to do was to do something in QoE. There's some other problems. It should be real time. It should be robust to video content and distortions. It should work for most of them or all of them. It should be simple and lightweight. It should not drain your battery. It should be independent of codec, because somebody uses Flash, somebody uses SVC, somebody uses MPEG. You don't have reference video, and it should be accurate. So we have a lot of constraints when you're trying to solve this problem. Most of the research is focused actually in spatial quality assessment. They try to assess a video as an image, and they try to assess the quality of that image. That's how most of the existing research in video quality has happened in the last 30 years. We focused on the temporal quality. What it means is when a person is moving, we're just trying to see what is the difference in the temporal fluidity of the video. We're not worried about the frame itself. We were worried more about the temporal fluidity of the video. And that actually makes more sense in today's era, because YouTube and all this content, they're based on HTTP. They're not based on UDP in the traditional sense, which was connection was less, and we had blocking and other errors. So if you have any channel losses, you have buffering. You don't have blocking now. Most of the times you have distortions which are like buffering, except Skype, which is obviously a real-time protocol. So 90% of the videos over the network are on HTTP. There we need a temporal metric, not just a spatial metric. So we try to focus on the temporal one, and actually we defined a metric. So we call it as a TVM, or temporal variation metric. and we use it to define another matrix, TVI. I'll give you the example here. So we have the frame P minus 1 and the frame P. We just take a difference and normalize it in the log scale. So this is a TVM. We try to see how it computes, and we try to see the existing metrics in the image processing community, apply them in a temporal way instead of spatial way. And we saw that our actually algorithm matrix TVM gives a very high correlation to optical flow. Optical flow is the accurate representation of fluidity in the video. What it means is, at a pixel level, you're seeing which pixel went where. So, but it's very expensive, you know. It's like compressing a video at a pixel level. So it's really very expensive to do it. But so that's the gold standard in this thing, and other reference metrics. And we see that TVM gives a pretty high correlation in like 90% to the fluidity of the video. But in terms of the running time, it requires much less time, and it requires much less memory. This is all in log scale, so it's not linear. So we have order of magnitude savings in computation memory, and it's giving very high correlation. So we chose that. We define a TVI, which is a normalization of TVM. So whatever we measured at the destination, in the smartphone side, we also calculate these values in the original video, and we take a difference and normalize it. So that is a TVI. So it's pretty simple, the matrix seems to be. But we find a very strong correlation to the QoE. So this is for one video, a park video, and we have different packet loss and network losses. And these are the subjective scores from the users. And we get a linear regression with the pretty much like 87 to 96% correlation. So it's pretty good. So now we wanted to scale it up. So we wanted to see how it works for a big data set with a large number of distortions and all those things. So we had collected, this is a data set released in 2012 or 13 by UT Austin, which has 10 representative mobile videos in 20 network settings and codec settings with 50 subjective evaluations each. And we generated 2 more data sets, and this one particularly has like 2,300. Last 3 years, the student actually collected almost all the movies released, the movie trailers, which are like 3 minutes. We have all of them, and we made like 183 participants. We could do subjective evaluation of them, and we did frame by frame processing for these videos. So we get a very big data set with a large number of distortions and resolution and GOP size and all the different varying parameters of a video. So that's what we tried to use. And I'm not going into the details of this slide, but the basic idea is these are different types of distortions, and TVI gives pretty consistent result, but it goes low here if you can combine everything together. And if these are different types of distortions, and it goes to like 70% correlation. So it's getting low now. It was not 90% like before, but it's getting low. So now we try to do some analytics more. So we try to compute some more features from TVM. We use TVM from source destinations. We calculate temporal information per second from these vectors, and we count how many times there's a freeze counts or INF, infinity values, in the TVM series. Because if there's a freezing, it should cause infinity values, right? So if there's a freezing, we wanted to detect it. If you see here, this is freezing, and we have least correlation for freezing, So we thought that we have to incorporate the freezing parameter into our decision model. So we incorporate INF. INF means the infinite counts. So let us say I'm watching a video, okay? If there's no freezing, there'll be motion in the video, and we get that as a value. If there's no motion, if there's freezing, the screen doesn't change, so the difference becomes 0. And log of 0 becomes infinite. So we get INF value as the output. So we just count that INF as an extra feature. And actually, when we train a decision tree with all these features together, we get a pretty high correlation, 93% now. And it still improves, but it's not enough for freezing. So we are getting a very high correlation for most of the distortions except freezing. So what we did, we tried to study freezing further. Existing work, this is a work last year in SIGCOM by Athula Balachandran, and they try to develop a quality of QoE for video, and they have a this is the fraction of content viewed because they don't have the exact scores. So they're using that as a model for QoE, and they see that at this threshold, people stop watching video, but then it's zigzag. So still, they are not certain what's happening in the freezing. That's what there's no modeling they're able to do in this figure. So we had to go more deeper. So what we found is that not all freezing is the same. Not all freezes are equal. What it means is It's not just enough that there's a freezing in the video. In 10 seconds video, there's a 5 seconds freezing. So the quality is bad. But the perception of the people about the video depends on the intensity and the position of the freezing. That's what changes the perception of the people. So if you see here, we have in psychology also primacy effect, that people tend to remember what happened in the beginning, and the recessive effect that people tend to remember the most recent information presented about a product above all else. So if you see here, we try to do this experiment. We have a video clip of 30 seconds. If you have a freeze here, here, or here, so beginning, middle, or end, and here it's distributed, right? So if you have this, we're changing the position of the freeze right now. And if you see here, we're changing the distribution. So we try to do a subjective evaluation with the users using these different types of freezing now, and see what model can we get. So if you see here, it's actually, if I'll go to the right one first, it's actually pretty close linear. If you have a beginning freezing, it has a very high impact on the quality, and as it is low, it's having less and less impact. So that's what we get from the subjective evaluations. And if you see here, we tried so 8 times freezing of 1 second each, 4 times freezing of 2 seconds, and 2 times of 4 seconds. So if you use just count the number of freezes, it's the same in all of them. But if you see what people say, its quality is 2, 2.5, 3, and it's the standard deviation. So we can see that there's a linear relationship we are getting here. So we wanted to model all these things together, and we do the linear regression model in this case, and we develop a QE model for just the freezing part. And if you see, it pretty closely matches the actual values. It gives an 81% correlation with a mean error of 0.25, which is pretty good for us. Now, there's another thing we try to evaluate here, that we always think that a higher resolution video should be better. But this paper, last year's 2013 paper, it says that the percentage of viewed video has a zigzag curve. So we tried to see what should be the reason. And we found that actually, if you increase the resolution only, it's pretty linear. There's no problem. So if you increase the resolution of the video, people say the quality is increasing. And there are hundreds of people who are doing that. So there's no problem here. So then we tried to see what happens when a network changes. And we found that as the network changes, people are more sensitive to the switches of the resolution. So changing network conditions, let us say my bandwidth increase, okay, and the content provider increases the resolution. It does not necessarily improve the quality that much, or it may do more than what is required. So we tried to do some experiments. So what we did is low and the high quality and the medium. We did 3 different qualities, and we did a resolution switch in the middle of the video. So low to high, high to low, low to medium, medium to high. And what we got is here. If your quality is increasing in the second half, people are getting a better perception of the video. So the green one here is a naive video where there's no switch of the quality. And the yellow is the one video where you're switching from the low to half. So the low part, people are giving this rating, and overall this rating. So if the video had no switch, it would have got this MOS, but because of the switch, it has got this MOS. So with the same bandwidth, because there's a switch, people are giving a higher perception. And if you reduce the video bandwidth resolution in the end side toward the second half, we get a lower bandwidth here. There's lower the quality rating from the people. So especially if it is a high to low. So if you have a high drop in the bandwidth, then people are perceiving. So in this case, let me just try to give a practical example. Let us say you are on a connection and you are getting a 1 Mbps bandwidth. But it's a fluctuating connection. So it's better for the company to give you only 500 kbps from the beginning, and you'll be more satisfied than they give you 1 Mbps in the beginning and 500 Mbps in the later half. You will give a lower rating because you are seeing a declining quality in the middle. People tend to remember that more. So that's what I'm trying to drive home from this one. So we tried to model this. So the problem here is the TVI values are pretty close, you know. So we cannot say how to differentiate which resolution is coming, because we only have one thing, TVI values. So we are trying to derive everything based on those values. But when we normalize them with the highest quality, we can see that the green, the red, they're pretty much nicely clustered, you know, on the top, linearly going down. And we use these normalized ones to drive the decision tree, and we get like 88% correlation to the MOS. So we combined all these 3 things together, and try to build a uniform model, which we try to call as video acuity, or the quality which you're actually viewing. And this is actual scores, and these are the predicted scores, and they're pretty closely in correlation with each other. So going back to the system, we have content providers, CDN, and the users. Now the users can give this model output to them, and they can, give them a better service. That's the basic, going back to the execution of the data. And it's lightweight. If you see here, an iPhone 4 and iPhone 5's implementation, for even an HD video, it takes less than a second, for 1 second of a HD video. So it's real time, and the memory usage is very low. It's less than 6 MB. And actually, you don't need that high resolution on the iPhone, because the screen for iPhone 5 is pretty small. So 720p is the maximum resolution you can see. And this result also we get from our data analytics, that beyond this resolution, if you show to people, they don't know what's the improvement in the quality. So there's no point of showing it, right? If you don't feel an improvement in the quality, there's no point in showing it. So this was an interesting result. We had actually 3,000 clips, and we did synthetic experiments to improve the number of clips, the number of this, and we did testing with hundreds of people. So going ahead, what we're trying to do is to develop an app which can act like a container for the YouTube app or something like that on the Android, so that you can watch whatever video you want, okay, on your network, on your home, wherever you want to do. And we will track the features we want. We have already developed some methodology now. So we'll track all these features on your smartphone, and we'll log it in our server. And at the end, we can just ask people what is the quality of the video you watched and what you felt overall. And we want to use that to refine our model and scale it to the real world, basically. So for more details, you can refer to these two papers. And we actually submitted a grant for the next part, doing the next part. And also we need to analyze, find more psychovisual factors, and see from the machine learning perspective how we can identify them and then address them, basically, to get an accurate QoE for the. So is there any question on this part?
How do you select the users?
So in this scenario, we tried. We had one database which is existing. The other thing, we wanted hundreds of users, and we couldn't get it so easily in the campus. So one of our students, he went to the church and he set up a Wi-Fi in the church room and asked all the people who are coming to the church, volunteers, that if you want, you can come there. And they did most of the trials. Because it's like 500 clips, even 30 seconds is like 250 minutes, right? It's a long time. So we couldn't do too many policies with this. So most of the church people, they helped us voluntarily. Yes.
You ran into jitter or
yes.
Is that kind of you're assuming it's not full time?
We are assuming that you will only increase the resolution when you have extra bandwidth. Like the companies like YouTube, they will not do otherwise. But even then, what we are focusing more was on the psychovisual factors, that if the bandwidth reduces, the person feels more at loss. So if it's a fluctuating bandwidth, better not to give him the extra quality because person is going to feel more cheated, right? So I agree that's a valid problem too. That if you just arbitrarily increase the bandwidth increase the quality resolution without an increase in bandwidth, you'll run into jitter problems. So I'll move ahead to the next part, which is the energy expenditure estimation. So we have a lot of new devices. This is a Fitbit a person is wearing and running out. And we have iWatch, Android Wear, Microsoft Launch, Microsoft Band. And I didn't get it. It's apparently sold out. I signed up and they sent me an email last week before Black Friday that we are going to ship it. And our grant person was trying to buy them, and he couldn't buy them. So apparently, I don't know how many they made, but they are sold out. This much is sure. So there's a lot of traction towards understanding the human activities and calories burned. This I'm just trying to give an example of a healthy person, and also for diseased population, the way they walk, their gait, understanding that, and also understanding their energy expenditure because that can help the doctors to give them better interventions and better consultation. So just some figures to draw the motivation that the chronic diseases is increasing in America. The national health spending per capita is like 130%, and the old population is increasing to the exponential rate actually now. So we need techniques in health informatics, in wearables, which should be able to provide this help to people in an automated healthcare, or whatever you call it, smart health, connected health, assisted living. So we need these technologies for this, and this is largely driven by data science along with the sensing part. So we also have a very high shortage of nurses, the availability and the demand for physicians and other specific nurses. So we have a shortage of healthcare providers in America, which requires us to go towards automation in a big scale. Going towards energy expenditure estimation, the idea is to measure how many calories you are burning and how much you're moving out. Because most of the diseases can be, prevented if you have an active lifestyle. Sedentary lifestyle is one of the major components for obesity and overweight population. And I think 1/3 of the American population is obese by the report stands, what the report says. So 1/3 is a very huge number. So we have many methods to do that actually in existing history. So direct calorimetry means they have a room like this. Whatever you do, it measures and it tells how many calories you burnt. But the problem is you can't do it for a common man. Everybody is not going to turn his home into an experimental lab with millions of dollars. The next thing is you use activity-based questionnaires. You give a form to people on the smartphone. It pings up now and say, how much do you eat? How much did you walk? How much did you do that? How much did you do that? But that's also not so practical because people will feel irritated and children can obviously not do it. We have indirect calorimetry systems like the COSMED. What it does, it's like oxygen mask. You wear it like this and it measures oxygen in and out, and it can pretty accurately, up to 98, 99%, tell you how many calories you have burnt. That's pretty good. But again, nobody's going to wear an oxygen mask throughout the day, right? So we are trying to do something practical. So there were a lot of heart rate sensors from different companies. Even Apple Watch has one. But by themselves, heart rate sensors are also not accurate, especially for low intensity activities. So the most accurate things are the accelerometers, and that's why you'll see a lot of surge of them with the companies like Nike Plus, Jawbone, and Fitbit, and things like that. So they can measure motion across multiple dimensions, and they're pretty accurate. Obviously, I'm also studying how the accelerometers fuse with different sensors to improve the accuracy further. So what we did some protocols. I recruited some people. This guy is wearing the oxygen mask, which is a COSMED, which is a gold standard or the reference value for us. And we made them do different activities, climbing stairs, walking, running, sitting, sleeping, and all those things to get different data sets. So the thing is, this COSMED is not like a computer science equipment. It gives asynchronous values, so we had to resample them and everything. Similarly, we have to translate the local coordinates of smartphone to global coordinates, and then we have to add some features. We have to do some signal processing on the obtained data. So we took an epoch of 4 to 6 seconds. We got some features from signal processing, transforms, and all those things. And we use all of them as a features to drive our research, basically. So what we would get is if you just use accelerometer data. So here what we tried to do was fuse accelerometer and barometer in the smartphone. Because beginning 2010, Google, and I think beginning 2013, Apple introduced barometer sensor in their smartphones. And this can help us a lot in the altitude. For example, if you're climbing stairs and climbing down and all those things, barometer is should be very helpful to accelerometer to detect all those things. So if you just use accelerometer data, it gives only 70% correlation, but it increases if you use barometer data and all the extracted features to 98%. So that's a pretty significant high. And these are the results in visual learn. So these are the blue is the line of how the person's activities are moving with time, how many calories he's burning. So the calories he's burning per second. And that's the blue line. The green one is a linear regression, and it's pretty inaccurate. And the red one is the machine learning model we obtained, and it pretty closely follows, not 100%, but 90%. And if you see here, these are the results of Nike Plus, Fitbit, and this is the existing calorimetry equation, and ours is pretty close to the gold standard. So actually, we try to do more things with the different data sets actually. So In this one, I'm just trying to say what is the improvement using just barometer, not other extracted features, and we see 71 to 83%. So barometer is helping us a lot. Similarly, if you see here, so this is all for healthy kids who have basically no health problems. But you also try to extend the analysis to the kids who had, and so the first one was with adults too. The second one is with kids who have a neuromuscular dystrophy called as DMD, where basically they cannot walk properly after the age of 5. They reduce their locomotion. By the age of 10 or 12, generally they end up in wheelchair, and actually they die prematurely by the age of 30 because of neuromuscular dysfunction. So our motivation is that if we can assess and help them in physical activities, the more activity they do, it's better for their health, and it keeps them more mobile for a longer time. So we try to see what are the features we are getting, and for DMD boys in different age groups. And if you see heart rate is pretty okay, consistent, it's fine. But if you see acceleration, the DMD boys, their acceleration correlates much less to the output than other population, you know. So this is because their motion is not the same as our motion. And even if you build a model specific to that data set, it doesn't serve the purpose. So for them, this sensor is a better predictor than just using an accelerometer sensor, for example. Similarly, there are differences in terms of age and height, other parameters. So this is basically information gain, which is from the information theoretic analysis. So we actually went a step ahead for the DMD population and built another machine learning model for that population. And we see that the existing models and the linear regression models give like 40% correlation, but our model gives like 91% correlation with the output. And if you see here, it's pretty accurate in terms of their energy expenditure values. So what we're trying to do now is utilize these methods to monitor physical activity, energy expenditure, and things like that. We're trying to expand our clinical trials to have a larger population of the DMD kids, because we had only 7 kids in the hospital to do this initial test. And we wrote an NIH grant to have a larger population, as well as to see might be we're not getting a result because they move awkwardly. So instead of placing a sensor here, might be if you place in the leg or a hand, we get some good results. So we want to study sensor placement as well as identifying the right sensors and for a larger population for them. We are also doing some work to study, you know, the function of these accelerometer based or these mobile wearable device based methods for the larger population. So we are running a trial right now where we have like 165 people enrolling. It's open enrollment, and we're giving them the devices for like 6 months, let them keep it, and we have health coaching, and we want to see what is the impact of health coaching and giving this technology to the people in terms of their improved health and engagement. So we are storing everything on our servers, and then once we have the data set, we'll be able to mine it. So are there any questions on this? So I'll just move ahead. So I'm just trying to draw the same slide back. So going to the big data overall approach, I find I work in these underlying areas where I actually do work, and I'm interested in working in data sensing and more on data analysis and sensing and doing those things together to coordinate more accuracy. For example, I just give the example of the accelerometer one, right? So most of the existing work before us, they were using a very high sampling rates and using a linear regression model and things like that. So that very quickly drains the battery of a phone. So we used, instead of 20 or 200 hertz, we used a sampling rate of only 2 hertz with barometer and other sensors. So that reduction of the sampling rate with the machine learning algorithms gives us a much higher lifetime of the sensor than using a very high sampling frequency. So things like that. And obviously data execution is obviously application specific. So going towards the future of research, are there some challenges I see 10 years from now or things like that? So one thing is, we were living in the age of megabytes. We've gone to actually we are only till petabytes, I think, most of us. And most of the industry, university research is in gigabytes. We are really not going to very bigger data sets in the universities. We don't have like clusters like Microsoft Cloud and all those things. We are not running most of the times. So we are mostly in mega and gigabytes. We're going to petabytes, exabytes. So, but the volume is increasing and increasing, and that leads to more and more challenging on how we process this data. The other thing is that data is becoming more and more heterogeneous. For example, in this scenario I just gave, we have data from your smartphone sensors, your Skype calls, your text messages, your voice calls. To make your profile, we need to integrate all this data now. And these are all very heterogeneous data, right? We are coming into the age of. So how to fuse a heterogeneous data set in large volume? That's another big issue, I think. Another important thing is the acceptance of data science itself. Because outside computer science, it's not that easy to get people to accept it as a science. They're more into theory and applications than they're using data science itself. I'll give a simple example. Last month, we were trying to do this trial, and I asked my PI from the health system, he's a doctor, and we were saying that let us put this more so that we have a lot of data, okay? We were trying to do a custom app and things like that, and some features. And he said, no, my experience has been that if we do too much collection of data, it doesn't help us ever. We just end up wasting time in collecting and we never use it. So let us kill it. So, you know, that happens a lot because people don't have at least faith, even at least today. Obviously, I think that this will change in the next 10 years or so with more different disciplines, putting more faith in this research and that leading to more interdisciplinary activities. And another thing will be like I was talking with the faculty here that about heterogeneity and the scale up of the hardware. So there was a paper last year by Microsoft in ISCA. It was in Minneapolis this year. And the paper was they're using FPGAs to accelerate their research, image search, and I don't know, data or image search. So the thing is, FPGAs are pretty fast and they're like custom chips, but not many supercomputers or cloud infrastructure support FPGAs because the programming is more close to VLSI than a software. So on a software, if you want to do that, it's pretty difficult. But Microsoft, they found like order of 10 magnitude when they were doing it on FPGAs. So they decided to go with it. They had like 1,000 computers and cluster of 1,000 computers, and they found very good results. And now they're wanting to put entire Bing search data centers into using FPGAs. It's still getting, after all the overheads of software hardware translation and everything, they're getting like 2x speed up over the traditional GPU-based computing. So now we have hardware, now we have software processors, we have, what do we say, the GPUs, and now we're FPGAs coming back into the rack of the supercomputers. So in terms of hardware, we have a lot of heterogeneity. Similarly, obviously, we have Azure as another open source platform. So we have a lot of heterogeneity in terms of hardware also, and that has to, so as it scales up, it gives more benefits, but we need to develop ways to do that properly. And obviously, one thing is securing the data and securing the cloud, because especially when you're sensing humans, the privacy is very important. I'll give you an example. You may think that if I'm walking and I'm getting some data from Fitbit, I don't care if somebody sees it, right? But most people do care, actually. When we did a survey, we had some focus groups with the School of Nursing guys. Most people do care that their data should not be leaked. Although on an individual level, if I ask most of you, you'll say, who cares, whether my data is lost or not? Yeah, I'm just walking. What difference does it make? But people do care. And especially if you want to do geolocation, it's very sensitive. So we have to work hard to securing and privacy of the cloud. So that's a basic thing. I just went through the department website for teaching and the possible courses I can be able to teach in decreasing order of preference. And it's the basic one. Yeah.
So the question, you mentioned the increasing volume of data becoming a challenge, and I wanted to tie that into the first part of your presentation, where certainly in streaming video, you also have a volume of data problem, and the streaming community solves that problem by various mechanisms to dealing with resolution of the video coming through and so forth. Are techniques to get by with less data dealing with the data volume problem and the video streaming problem, are those the same problem, do you see, or similar, or are they very different? And
I think it will be different for data and video, because video is the problem mostly in the mobile networks. The companies or the enterprises, they are not worried about this problem. It's mostly the communication networks and the cloud for Microsoft or Google who are worried about that. But for the enterprise customers, it may be a different approach.
But are some of the techniques of sort of not dealing with all of the data, just dealing with a sample of the data and coming up with acceptable results, right? For
Yes.
video, the acceptable result is that somebody can still have
Well, the tools will be the same. The
right?
tools will be the same, but the application will be like very unique from, I think, the application specific way to make it more fast. Okay. Yeah.
Yes, okay. So based on your presentation, it looks like you mainly worked on the quality issues of video transmission over the mobile network, which for the main purpose is for the users of sharing the videos. So what's beyond that, in terms of the videos on the mobile network, beyond the sharing?
No, I'm working on a number of projects actually. I just highlighted one or two of them because it's only 1 hour. Like I'm working right now on a project on where we have data, a very big data set from a telecommunication company from China, which have given us the log of the network service they provide to different users and which users complain back to them. And the goal now is to, first of all, develop a prediction model of when a user complains. And then, so that's the first part, which requires a big data analytics. And the second part is going back to the network and reschedule the network using these inferences. So we want to change back the way the scheduling of cellular networks happen using these parameters as input. So in another project we are working on, I said about the health informatics, where we are trying to collect data from people individually and also in the population level and use machine learning tools to draw inferences. So in the individual level, it is like energy expenditure or calories out, but in the population level, it is toward the trends and what people feel comfortable and things like that. Thank you.